So actually the answer for painting, yeah, you can do it. And Cynthia unfortunately cannot make it, but she's producing graphene ink. And definitely you can use it to paint. And actually we did last year some exhibition at Mozy where there was artists painting kind of graphene ink related stuff. So it is doable nowadays. And to make a comment on what you just said, I'm pretty sure there is some graphene because it's probably carbon black and you do have graphene inside. So for sure there will be something. But today I'm going to talk a bit about what I'm doing at the University of Manchester. So I'm looking at the nanosafety of particles, and I moved from carbon nanotubes to graphene, looking at what is really topical at the moment at the university. So I'm going to move from purely the science, and by exposing biological system to the graphene, you will see that we are able to produce really nice objects, pictures, and interaction between the material and biological system. So as you know, nanomaterial, there is many properties. There is also starting to appear many applications, and all these applications coming from nanomaterials and graphene mean that humans will be more and more exposed. And when I'm talking about exposure, I'm talking about the three main routes of exposure. So the topical, because actually people start to think about having a tattoo made of graphene to have more interactive tattoo. You also have ingestion that is taking place in some places, and I will show you one example of graphene that you are actually already eating. And there is also going back. And also the main issue, which is inhalation of nanoparticles that are in dry or powder state. So the main issue is the exposure, and is it safe or not to be exposed to this nanomaterial, and in this particular case, graphene. So all the context is coming from whatever you have heard about the air pollution, the fact that there is roads all over, there is a flight as well that are releasing a lot of particles, and most of them are nanoparticles. And what is really not well known is the real impact of all those particles and nanoparticles on health, because we know that there is, because of this exposure, there is disease and sickness appearing. So we want to have the pure connection from the fact that they are nanomaterials to the disease. And actually there was a paper last year talking about the fact that alongside the traffic, they were able to find carbon nanotubes, but not only in the air, but in the lung of children, actually. So they found some carbon nanotubes in the lung of sick children because, yeah, they get access to these samples just because the children were sick. So they were going down to diagnose what was going on, and they found some carbon nanotubes. And I'm pretty sure that there is also a bit of graphene also if you look really in depth, but it was just much easier to find carbon nanotube because of the structure, the multi-layer thing. So already there is this kind of exposure. And another one, which is a well-known fact, is that when you are grilling, you are actually producing a lot of carbon material. So there is already a lot of amorphous carbon, but you are also producing carbon nanotubes, furans, and graphene. So and that's probably why actually it's not so great to eat the black part, because it's carbon material actually that you are eating. So if you can reduce this part when you are eating, that will be probably much better for all your digestive tract. Yeah, really interesting. But actually there is not so many people looking into what is the real connection between this big part of the meat and the impact on all the disease. So what we are usually doing is trying to assess the real risk, and for that you need the exposure, and we are also checking the hazard. And the aim is also to identify emerging risk, describe new model to have more predictive toxicity, because you have so many nanomaterials that it's just impossible to test them all. So we need to have more predictive models. So that's why we are still doing some assessment, but for reference material. And then from this reference material, we will be able to extrapolate to what could be the risk for the new ones or the ones that are around, but that are quite close to the one. So based on the physicochemical characteristic of those, and the link with the hazard of the reference material, we will be able to do the correlation via computational model. But also the aim of the whole community, so which is a European effort via the nanosafety cluster, is also to propose solutions for the exposure, but also solutions to reduce the hazard, and eventually by also modifying the way we are using nanomaterial, we'll be able to prevent any disease to happen, and to repeat what happened with asbestos, for instance. So by gaining the knowledge on the interaction between materials and biological system, we will be able to use nanomaterial safely. So first, we need to look at the interaction between biological systems, so either the whole body or the cells, and the material. So where does the interaction take place? So it could be inside the cell, and if it's inside the cells, it's quite complex actually, because all this stuff are going on all at the same time, and if you look at the real structure of the cell, it's that busy. So when you have these teeny things going on inside here, it can mess up the whole process and all the things that are going on inside the cell. So when you try to understand what's going on, it's really tricky, just because there is many stuff and many processes and functions going on all at the same time. But it could also take place outside cells, so between cells and or really close to the cell, which is the real surface of the cell. So that's the cell membrane. You have the internal part of the cell that is here, and that's the external part, so the really near region of the cell, what is the surrounding of the cells, and nanoparticle can interfere with that, and then the cells, because as you can see, the cell is connected to the outside via this receptor, then if there is interference in that region, then it's the whole communication between cells and the outside of the cell that can be completely damaged. So what matters at the body level is also the distribution of the nanomaterial. So when you have been exposed and the nanomaterial is traveling across the body, so what is really interesting to know is the distribution and where the material is accumulating, if it's removed, clear from the body or not. And in that case, if it's not clearing, what is the interaction with specific organ of accumulation? So the lung, the heart, brain, liver, spleen, and kidney are the key ones that we are looking at. And also what is also key is the interaction with the immune system in all these organs, and also the blood compartment, because usually that's the way nanomaterial will travel through the body. And at the cell level, what is important? So in that case, it's more the material that is really important. So what we really need to know is the intrinsic property of the material, but also the biological identity of the nanomaterials, which is not so easy to understand, but basically, when you have your material going inside the cells or close to a cell, then it will be covered by whatever the cell is secreting. So there will be protein going around and surrounding the cells, and you will end up with not a pure bare material, but something that is coated with protein, and that's what we call the biological identity. And that's the biological identity that will interact directly with cells or tissue, and that will trigger a response or not. What is also interesting to know is whether the material is going inside the cells or not, and the specific location within the cell. So if we look at the material, what is important when you are looking at the toxicological effect of material is actually all these properties. So whatever properties a nanomaterial can have may actually impact the cells, how the cells will respond to the tissue. So in terms of translocation, tissue accumulation, the toxicity, the clearance, and the secondary organs. So whatever the material is made of will be important in terms of response from the cells of the tissue. Then that's the material. You have seen it already in the previous session. So the graphene, it looks flat. That's the graphene oxide. That's the main one we're using because that's the aqueous version of graphene, because graphene is so hydrophobic that it's really difficult to use it for this kind of study. So what we use is mainly graphene oxide. But that's how it looks like in theory, but that's the reality of it. So what we are using is actually a material that is not that flat, that is completely wrapped into some kind of tube. Sometimes it's just mesh. So it's very not so flat, not two-dimensional. No, we have actually something that is close to a 3D structure. So it's actually indeed flat when you put the material, so graphene oxide, into water. But as soon as you move from pure water to something that is close, so in that case, that's physiological solution. So you have something that starts to appear, and that's some small aggregates. And when you move to something that is more relevant for what you want to assess, definitely you have huge aggregates and huge interaction between the materials. So that means that when you are testing, what you need to consider is those materials and not the 2D material. Then we have the biological component of the interaction. So in that case, what will be important is the form of it. So if it's in dry powder, colloidal suspension, or as substrate. And I will show you that for each of them, we have generated some really nice picture when there is interaction. So the first thing to look at when you are talking about dry or suspension is the interaction and the way the material is going inside the cell. So there is a lot of studies trying to understand the way material and graphene in particular is going inside the cells and where it's landing, then if it's going in the nucleus or if it's just staying inside the cells or in some vesicule or where is actually staying when it's inside. So that's few examples of what you can, so in that case we use a cell that is, the job of these cells is actually to eat all the dust around, even the dead cells, to clear. And in that case, we're exposed to graphene. And you can see with the bright field is that the material, because it's slightly brown, when it's accumulating, then the cell just turns into black. And when you look at it, you have what is white is the nucleus, and what is black is actually the whole cytoplasm completely full of material. And you can do exactly the same, but without another any labeling, and in that case we use Raman microscopy, and you end up with exactly the same. So whatever is the really blue region is actually the nucleus, and what is green is actually the specific Raman signature of the graphene oxide, and that's how you end up with this picture that look very much the same. So if you end up with a material that eventually is not black, you will still be able to track it via this type of microscopy. We also did the same, but this time in confocal way, so we can eventually, not with this cell, because these cells are so full of material that there is nothing really to track, but when you reduce and you have really small amount of it, using 3D dimension and the fact that you can have tomography, we will be able to see really where the material is going inside the cell. And you can also use transmission electron microscopy, so that's the material outside the cells. So when it's interacting just with the liquid of the, in which the cells are suspended, and that's the interaction. Oh, sorry. So here you have probably few flakes, so let's say about 2 or 3 of them that are directly interacting with the membrane, and the cells is probably trying to engulf the material inside the cells. And that's when it's inside, so it's not that easy to actually understand what is what here, and that's why usually we couple this kind of imaging with some analysis. So we do some diffractions, and we are able to reconstruct when it's in the good plane, actually, the nature of the material that we are looking at. So there is a way to couple and to really confirm that indeed the material is inside and still have the proper structure of graphene or graphene oxide. So then I will not show you all the way material can impact the cell, but I will just summarize when the material is inside, what it could trigger. So you can have oxidative stress, so basically the cells is so stressed that all the oxygen inside the cells and the species related to oxygen are reacting, increasing, and that can damage all the processes that are going on. So when you have increase of this reactive oxygen species, basically you can induce apoptosis, which is the death of the cells, but you can go slightly lower than that, and just damage some part of the cells that will, over time, over a long period of time, especially if it's chronic exposure, damage and induce disease. So you don't always straight away induce toxicity, so cell death, but you can induce something that is in between, which is in some cases more damaging than cell death, which is actually a normal process of getting rid of something that is not viable anymore. And the kind of outcome that you can have is the chronic inflammatory disease, fibrosis, and also cancer when the material is accumulating and keeps stressing the cells. And you can also have pulmonary and cardiovascular also disease. And that's the way it's working. So basically, according to the amount of this reactive oxygen species, you will induce different type of reaction, and one that is less damaging, the cells can recover, another one where the cells are really in inflammatory stage, which can trigger a lot of disease, and the last one, which is completely overcoming all the reaction, the possibility to defend itself, so nothing can happen anymore, and it's going to cell death. Then let's move to another part. So in that case, it's not so much related to nanosafety, it's more related to biomedical applications. So when we want to use the graphene as a layer on any implants or prostheses, in that case, we put cells on it and see the reaction of it. So that's just a pure model. So in that case, we use CVD graphene that was placed on glass, and we put the cells on it. And that's what you can see. So the cells are kind of really happy. They are growing completely well, completely covering the whole substrate. And in some part, for those who are working with graphene, they know that transfer of CVD graphene is not that easy, and sometimes you have break. So that's what you can see. So yes, it's amazing. You can see a one-layer atom only in one piece of glass. So that's what you can see is the one atom thin layer of graphene that is just detaching from the glass. We did the same, but this time on silicon dioxide, just because it's a bit more pretty when you look at the cells. And that's how the cells look like on it. So the same, what you can see here in real purple is actually the graphene layer underneath. And the cells are still growing really fine on it, and they look quite pretty, and you can see completely the nucleus over there. And you can even see the protein inside that are working for the structure of the cells. So the fact that the cells have this shape is down to these proteins that are really nicely aligned like tubes. And that's the kind of imaging that you can just looking at the cells on the CVD graphene. So in that case, we move a bit further using a reduced graphene oxide. So you have your graphene oxide in suspension, then you coat on a piece of polymer in that case, and then you reduce that, and then you put your cells on it. So that's why in that case it's not one layer only, and it's quite thick and it's quite dark and reflective at the same time. And you will see that that's how we end up with really nice picture as well. So that's the material that when you do characterization with atomic force microscopy. So it's not flat at all. As you can see, there is a lot of valley and hills or ridge and wrinkles everywhere. So it's quite disturbing for the cells, but also at the same time quite good because you can have a lot of protein going on and a lot of attachments. So it's quite nice surface to work with. And that's the material when you look purely at optical microscopy, just the fact that it's slightly reflecting, you have this very nice kind of picture where you do have cells here. And if I zoom in, that's here over there. So on the one part of what you have seen before, you can see some cells over there that are attaching nicely with the nucleus right in the middle, and then the processes all around. So that's the kind of imaging that we can achieve when we are looking at the cells on substrate. So now we'll talk a bit more about what's going on in Manchester in terms of arts. So that is actually what the university used in terms of communication to talk about a science paper that was published 2 weeks ago about the whirlpool in graphene. And you can see that there is people that are quite creative in Manchester for working around graphene. And that's what we are also trying to bring from purely academic to Well, actually, I can show you the building. So that's the Graphene Institute. So over there will be some display about all this possibility that we will create in the labs. So that will be exhibit over there, because down there you have the clean rooms, and over there is some kind of white walls. So you will be able to see the clean rooms downstairs, at the same time projection of all the work, or the artistic part of the work that is going on. And that's one of the creation that is actually in the entrance hall. I'm not sure you can see it really nicely, but it's actually a hexagon that are engraved into, and it's going from the bottom to the top of the building. So there is a place for art inside this building, and the whole building is quite really nice, to be honest, compared to all the other building. And also the undergrades. So we have a society, so that's the logo, and that's one of the banner. Yeah, no problem. Yeah. So that's an invitation if you want to join. This year we have we are European City of Science, and there is the European Forum. So you can come, and there will be place for arts in science, and also everything around, because we are the graphene city, so we are going to talk about graphene during that conference and doing that quick. And definitely we are trying also to have this art exhibition around graphene for presenting this kind of work, or also this, which is an advert for one of the exhibitions that the two Center for Doctoral Training are going to do. So they will talk about graphene and space in that case. So the two doctoral training, and that's the adverse, talking about graphene and space. And thank you for your attention.
Why do you think these carbon species like graphene or whatever are absorbed by the cell somehow? Is there any reason? Is there any particular chemical reactivity that allows them to enter, or?
We do not have all the answer about that. So in terms of internalization, especially because now we are actually able to work with pure graphene, because we are able to have some surfactants, so we have some kind of suspension for graphene. So we are comparing graphene oxide versus graphene, and it looks like the cells are still able to internalize it. So in terms of chemical function, it's not quite clear what is important. Probably the charge is important, but also the fact that you have some groups on the surface will be also important. So to interact with those receptors that I have presented.
Okay, thank you.
Please.
Since graphene oxide is charged, you have a lot of OH groups and carboxylic acid groups. Does it matter for the toxicity if you have different charge balances by metal ions or by, for instance, positively charged peptides or polypeptides?
So you mean if we further functionalize the graphene oxide with something like amination?
Or if you look more as a hybrid material, together with biological components. Yeah.
When you functionalize graphene or graphene oxide, you end up by decreasing toxicity.
Okay.
Because you kind of decrease the negative charge in the case of graphene oxide, so the reactivity is not exactly the same. So the fact that you balance and go to something that is a bit more neutral, so still charged but a bit more neutral, is slightly better, as it appears. But in the case of when you have these hybrids, usually you are not really checking the pure nanosafety for it. You are actually checking biocompatibility for one specific application, which means that you will use your material with specific cells in a specific location of the body. So you will not have the whole answer. So you will conclude on the fact that the material is much better for this type of cell in this particular location, but not for environmental exposure.
Okay, thank you.